Previously, I mentioned that a lot of these complexes have a distinct color to them. And that color arises from transitions in the d orbitals, from the T2G to the EG orbital. Now, I have some examples of some cobalt complexes here that I've synthesized. And I just wanted to show the color of these complexes because they're kind of neat to look at. So this first one is a nice orange color, and it is hexaamine cobalt 3 chloride. So in this case, since there's 6 amine groups on there, it's going to be definitely a high field or low spin ligand or complex, because amines are a very high field ligand. So this will split these into a big difference there. So let's look at how many unpaired electrons this complex would have. Now this is cobalt 3, and cobalt is, let's count over, that originally starts out as D7, I believe. Yes, originally it's D7. But then we have a cobalt 3, so there's a +3 charge. So we're going to lose the 4s electrons. So let's just start out by writing the electron configuration of cobalt. So we're going to have our argon, inner shell, and then initially we'll have a 4s2, 3d7. This is for cobalt. Now, we just have to remove 3 electrons to get to our cobalt 3 plus configuration. So not dipping into any of those lower not valence electrons. And then we're going to lose the 2s orbital electrons, and we're going to lose 1 d orbital electron. So that will leave us with a 3d6 configuration. Now, if this is a low spin configuration, our EG orbitals are quite high up because those ammonias are a good base, and so it's feeding in a lot of electron density from that Lewis base. So we're going to draw the T2Gs a little bit lower. And we have 6 electrons. So there's 3, 4, 5, 6. So in this case, we would have 0 unpaired electrons in this complex. And that would be what we would call diamagnetic, or it doesn't interact in an attractive way to a magnetic field. Now, let's look at some other complexes. Now, I'm not sure if these are actually high spin or low spin, but they're definitely a different separation between the two, because these have only 4 ammonia groups on them and 2 chlorines. Now, chlorines or chlorides are a low field ligand, so at the very least, these orbitals are closer to each other. Now, whether it's close enough for them to be high spin, I'm not sure. But let's just see how many unpaired electrons we would have if they were high spin. So if we did have a high spin configuration, these orbitals would be closer to each other. Let's see, here's EG, and then T2G. much closer to each other. And in this case, we're going to fill up like this, and we'd have 4 unpaired electrons. And so the way to measure that would be, again, to perform a magnetic susceptibility experiment on these and see. And we should be able to tell quite readily whether this is whether they are high spin or low spin, or high field, low field, depends. Simply because we have 0 unpaired electrons, so we won't see an effect from this complex. And we have 4 unpaired electrons, so we should see a very large effect in this case, because 4 is very close to the maximum number of unpaired electrons we can have in a transition metal complex. It only goes up to 5, since there's 5 orbital positions.